So we have a function f from z mod 6z to z mod 2z defined by f of the congruence class a plus 6z is the congruence class a plus 2z. So we want to show this is well defined. So that what that means is, suppose a plus 6z equals b plus 6z. So that means that a minus b, or a is congruent to b, mod 6. So 6 divides a minus b, which certainly implies that a minus b, a is congruent to b, mod 2. So f of a plus 6z is a plus 2z, and b plus 2z is f of b plus 6z. And because a is congruent to b mod 6, a is congruent to b mod 2, so these are the same congruence class. So this means that the function f is well defined. No matter what representative of a congruence class you choose, the function f sends that congruence class always to the same place. So f is well defined. The kernel of f.
Do we not have to show it's a homomorphism?
Oh, I'm sorry. I just saw the word well defined. Yes, we have to show that too.
Do we have to show that it's a group?
No, we know these are groups. You couldn't have you can't even talk about homomorphisms if you don't have a group. So we know these are groups. That's not a problem. These are additive groups. So if we take two congruence classes, a plus 6z and b plus 6z, I have to show that f of the sum is the sum of f of each of them. But of course, this is the congruence class a plus b plus 6z, which is equal to the congruence class a plus 2z, which is a plus 2z plus b plus 2z. So that's f of a plus 6z, because that equals this, plus f of b plus 6z. So therefore, f is a homomorphism.
So what I was missing in part A was just proving it was well defined in the email that I sent you, but my proof that it was a homomorphism was fine.
I don't recall.
Okay.
For part B, the kernel of f, it's all congruence classes a plus 6z, such that f of a plus 6z, which is a plus 2z, is the zero congruence class 2z. And this just means all a plus 6z, where a is even. Right? A plus 2z is 2z if a is even. So we have three congruence classes, 6z, 2 plus 6z, and 4 plus 6z. So the kernel is this set of three congruence classes, which is a certain subgroup of order 3. So that's my K. And G mod K, well, there are two left cosets, right? Because Z mod 6Z is a group with 6 elements. This group has 3 elements, so the index is 2. 2 times 3 equals 6. So one coset is K itself, and the other is, just for example, take 1 plus 6Z plus K. So that just means the cosets 1 plus 6Z, 3, and 5, 1, 3, and 5. So if I just write bars over the elements to indicate congruence classes mod 6, I have 0, 2, and 4. That's what K is. And the other coset is 1, 3, and 5. So the quotient group, it doesn't ask for the order of the quotient group, it asks for the quotient group. So the quotient group is the left cosets of K, and there are exactly 2 of them. The congruence classes of 0, 2, and 4, that's K. And the only other coset is the remaining, the odd cosets, 1, 3, and 5.
Can we also do number 19?
Yes, why not? So oops, where's the top of the page? There it is. So number 19 is, we have the permutation sigma 1, 2, 3, 4, 2, 3, 1, 4 in the symmetric group S4. What is the cyclic subgroup that this generates? So you have the identity, you have sigma. What is sigma squared? So let's compose them. Sigma squared is, actually, I can write this slightly more simply because this is 1 goes to 2, 2 goes to 3, 3 goes to 1, and 4 goes to 4. So I can also write sigma as a 3 cycle. It's just 1, 2, 3. So this is 1, 2, 3, 1, 2, 3. This sends 1 to 3, 3 to 2, 2 back to 1. That's what sigma squared is. What is sigma cubed? So sigma cubed is sigma times sigma squared, 1, 2, 3, 1, 3, 2. That sends 1 to 1, 2 to 1 to 2, 3 to 2, 3. This is the identity. So sigma cubed is the identity. So this is the cyclic subgroup. Generated by sigma. And the order of H is 3. Is H a normal subgroup? Well, I don't know. Is H a normal subgroup? Well, normal subgroup would mean every left coset equals a right coset. How should I try to figure that out? Any suggestions? Well,
see if you do like E sigma equals sigma E, and then see if sigma sigma squared equals sigma squared sigma.
well, I'm not sure why you're looking at sigma squareds. So if you multiply, H is a subgroup. So if you multiply it by anything in itself, it just gives you back the subgroup. So let's, for example, let tau be the transposition 1, 4. So for a transposition the inverse is equal to itself. So let's try to compute tau sigma tau inverse. So that's 1, 4, 1, 2, 3, 1, 4. Let's just try and figure out what that is. So this sends 1 to 4 back to 1. 2 goes to 3. 3 goes to 4. 4 goes to 1. Let's see, no, that's not right. Yeah, 4 goes to 1. 1 goes to 2. 2 goes to 2. So tau sigma tau inverse is this 3 cycle. So, so sigma is in H, but tau sigma tau inverse is not in H. So H is not normal, because if a subgroup is normal, it is it contains all of its conjugates. 2, 3, 4 is not a permutation in H.
And the index of H and G
So the
is,
index of H and G, this is for any subgroup, doesn't have to be normal, it's just the cardinality of G divided by the cardinality of H. G is S4. So that's 4 factorial over 3. 24 over 3 is 8. So the index is 8.
for a
Professor?
number, go ahead.
No, no, go ahead. You can complete it.
A quick question for number 15. In order to compute the congruence classes in the multiplicative group Z mod 7Z X, we would generate, like we would take 3 and then do 3 squared and see how many would each get in for each of those, right?
Right, you look for the lowest power. You start taking powers of 3 until you get to something which is congruent to 1 mod 7.
And you have to do that for each of the groups, right?
Well, not if you, for each of the 6 elements in the multiplicative group.
That's what I meant. Okay, that's it. We don't need to do that one though.
Yeah. But I mean, it's pretty easy. 1 cubed is 1. Sorry, 1 to the first power is 1. 2 cubed is 8, which is the same as 1 mod 7, and so on.
Do you include 0, or does that X indicate that you don't include 0, or does that indicate it's a multiplicative group?
No, that means the non-zero, well, in this case, it means the non-zero congruence classes.
Okay. Thank you.
Actually, on the same question, can you just refresh what congruence class is for that? Is it all the elements that form a cyclic group? No.
Are you asking?
It's the same question. How do you define the congruence class for Z mod 7 multiplicative group?
Well, no. So we have Z mod 7Z, which is actually a commutative ring. So which means, among other things, this is a abelian group under addition. But you also have the elements which are multiplicative. It's a ring, and under multiplication, 1 plus 7Z is the multiplicative identity. And Z mod 7Z with this time sign, this is the units in Z mod 7Z. What that means, it's all the congruence classes A plus 7Z such that there exists a congruence class Z plus 7Z, so that when you multiply them, you get the identity. So A plus 7Z has an inverse. Or if you like, that's all A plus 7Z, such that AX congruent to 1 mod 7 has a solution. And that's all the numbers, all the congruence classes except 0. So A plus 7Z is the non-zero congruence classes.
Oh, so okay. No, sorry. I get it. I get it. Thank you. I had a question about the question 14, which is let P be a prime number. Prove that if GCD of A and P is 1, then A power P minus 1 is 1 mod P. Now, if this kind of question were to be in exam, can we simply use the Euler's reduced modulo, basically use that function, the
Well,
phi
what
function?
this says is prove the Euler-Fermat theorem. So
Okay,
you can't say, well, it's true because of the Euler-Fermat theorem. I'm asking you to prove it.
okay, got it.
Professor, can you go over number 21 from the review, please? 21. Thank you.
So H is a normal subgroup of a group G if, first of all, H is a subgroup, and second, XH equals HX for all X in the group. Every left coset equals the corresponding right coset. And when you have a normal subgroup, if H is normal, the quotient group, G mod H, is the set of left cosets with multiplication defined by XH times YH is XYH.
Yeah,
Right? So those are the definitions.
no. I
Is
know.
there a question about this?
Question 18, part D.
Sorry, so is this okay for 15? Or sorry, for 21?
Was there, I think there was another part to that as well.
Okay, so let me do that then, before I go on to another question. So number 21B is prove that if H is a normal subgroup, then XHAX and X inverse is in H for all X in the group. Prove this. So if H, so let H be normal and let X be some group element, then because H is normal, XH equals HX. So for all H in H, we have X times this element H. This is certainly in the left coset, XH, which is equal to HX, which means there exists some element H prime in H with XH equal to H prime X, which means XH X inverse is this element H prime, which is in H. And that's what we were asked to prove. If you take an element in H, in the subgroup H, and an element in the group X, XH X inverse belongs to the subgroup. So
Okay.
that is the little proof of that fact.
Professor?
Yeah,
Question 18, part D. You don't need to do it. I just had a question. It's giving us a permutation sigma and asking for the inverse. Wouldn't that simply be just flipping the permutation? Sort of just reversing the permutation.
which question?
18, part D.
Well, I'm not sure what you mean by reversing it, but
So
the
one goes
inverse
to
is in some
4.
sense, you
Then
have to
4 would go
compute
to
the
1 in the
inverse.
inverse.
What?
I'm saying, so let's say in the original permutation 1 goes to 4, then the inverse would be 4 goes to 1.
Correct.
So you just reverse basically the top, flip the top row and the bottom row, and it gives you the inverse. That's what I meant.
Oh, and then you have to rearrange it. So the top
And
row
rearrange it, of
goes
course. Yeah.
1, 2, 3, 4, 5, and so on.
No, of course, but conceptually just flipping it. That's what I was
Correct.
wondering. Okay. And then question B, part B and C. So part B is writing sigma as a product of disjoint cycle. So that we have done one of those problems in the class or in the problem session. So I know that. But then part C is take each of those cycles and sort of decompose them in terms of transpositions. Is that what it is?
Yeah.
So let's say if you're okay.
Yeah, it's like if you have the 3 cycle 1, 2, 3, I can write that as a product of 2 transpositions.
1, 3, and 1, 2.
In lots of ways. I think 1, 2, 2, 3 works. This sends 1 to 2, 2 to 3, 3 to 1, for example.
Okay. So is there an easy way to sort of decompose any cycle?
Yeah, I mean,
Like what you just did, sort of?
well, I mean, if you have the cycle 1 up to n, let's see. I think I can write this as a product of n minus 1 transpositions. Let's see.
I mean, I know you have this in your notes, but it was kind of a little hard to follow
Well,
that component.
Yeah, I mean, I don't remember how I put it in the notes, but there usually are a lot of ways to do it.
I think in your notes, if I remember correctly, it's like transposition 1n, then 1n minus 1. So sort of like move everything by 1. and sort of reverse and repeat. I mean, rinse and repeat kind of thing. So one goes to n, then n goes to n minus 1, etc., or something along that lines.
So I think what always works is 1n minus 1, 1n minus 2, 1n minus 3, down to 1, 3, 1, 2. Of course, this will send 1 to 2, 2 to 3, 3 to 4. Oops. Sorry, this should be 1n. 1n, 1n minus 1, 1n minus 2, and so on.
Okay. Thank you.
Professor, I have a logistical question.
Sure.
What's the latest date, well, the latest whatever time I can hand in the missing homeworks? Because I still owe like 4.
Anytime over, I have to turn in the grades, I think, by Monday. So anything you get in by Monday morning is okay.
All righty, thank you.
Professor, can you actually display or go over compute 18D? Because I had thought of it in a different way. So can you just do that? Thank you very
Sure.
much.
So the permutation sigma is a permutation in S7, 4, 5, 2, 7, 3, 1, 6. So what is sigma inverse? 1, 2, 3, 4, 5, 6, 7. So the idea is, you look here, 6 goes to 1, so the inverse has to send 1 back to 6. 3 goes to 2, so the inverse has to send 2 back to 3. 5 goes to 3, so the inverse sends 3 back to 5. 1 goes to 4, so the inverse sends 4 back to 1. 4 back to 1. 2 goes to 5, the inverse sends 5 to 2. 7 goes to 6, the inverse sends 6 back to 7. 4 goes to 7, the inverse sends 7 back to 4. So
Thank you.
that's the calculation.
Professor, I think you may have already answered this question, but question 19C, which says justify your answer whether H is a subgroup or not. And I think it's talking about a 3 cycle in S4. So would simply showing that, a conjugate of any random element in S4 doesn't belong to that cycle, 3 cycle, would that be justification that, it's not a normal subgroup?
So that's exactly what I did.
Okay.
So is H a normal subgroup? I took, for example, the transposition 1, 4. When I
Right.
conjugate sigma by that transposition, I get a cycle 2, 3, 4, which is not in
Not in
H.
there.
So
Yeah,
H is
okay.
not closed under conjugation, so
It's not
H
normal.
is not a normal subgroup.
Will the final also have somewhere around 10 or 11 questions like last time, or more?
Excuse me?
Will the final also have like 10 or 11 questions like the last time?
I think I have, last time there was 1 extra credit problem. I think this time there are 2.
Okay.
Anything else?
No, thank you very much, Professor. Thanks for all the help.
Okay. All right, well, if there are no more questions, I will go back to making up a calculus final. So I will post the exam on Blackboard and email it to you shortly before 3 o'clock. And just like the last exam, it'll be due at 7.